TensorNetCanvas is a web application with an infinite 2D plane on which we can create tensors and tensor networks. So let's create a few small tensors as an example. Maybe we'd like to start with an identity matrix, 2 by 2. Maybe we'd also like a few other matrices, like a poly X matrix and a poly Z matrix. And maybe we'd like a vector as well, something that is similar to a ket1 vector. I can hit create, and we get the 4 tensors. And the first 3 are 2 by 2 matrices, so they are rank 2 tensors. That's indicated by the fact that there's 2 tabs below each tensor, so each of these tabs represents an index. And the last one's a rank 1 tensor or a vector, so it just has 1 index. We can drag and drop between the indices to connect them. And if we wanted to now, we could contract this tensor network. But before doing that, maybe we'd like to give names to these tensors. So I will delete everything and go back to this text box and change the syntax I'm using. I'll put parentheses around my definitions, and then I can add names. So maybe I'll call the first one I for identity. The second one we can call X, and the third one Z, and maybe the last one we'd like to call ket1. So we can do that. Create again. Now there's a little name in the upper left corner of each of the tensors. Just as before, I can connect them. Okay, and then I can hold down the control key and drag with the left mouse button to perform a rectangle selection. So I can select these 2, and then click on the contract selected button. That will contract these 2 tensors and replace them with 1. I can do that again, contract, and now if I hit F, we zoom in on that tensor. You might recognize this as a negative ket0 tensor. As we work and as we modify the tensor network, the state of the network is encoded in the URL. So we could actually bookmark this URL. We could share it with someone in an email or a text document, and if they click on this link, it should open up the web application and reconstruct the same tensor network in the same state. We can also hit the back button on the browser to undo. So by hitting that repeatedly, we can go back to a previous state. And now I'll show you a different way that we could contract the network. Instead of doing it 2 tensors at a time, we can select everything and then hit the contract selected button, and it does everything in one step, and we get the same result. So I have some other examples I've prepared, which we can take a look at. So the first example here is 2 vectors. Their indices are connected. So if we contract these, that's like doing a dot product. And we should end up with 0 times 3 plus 1 times 4 plus 2 times 5. And we get that. Here is a matrix multiplied by essentially a column vector. So if we contract those 2, we get the result of that multiplication. Here we have 2 vectors that are not connected. If we press the contract button, in this case, we'll end up with a tensor product. And because it's a tensor product on 2 vectors, it's the same thing as the outer product of those 2 vectors, so we'll end up with a matrix. Here we have a Hadamard matrix multiplied by a poly Z matrix multiplied by another Hadamard. If we contract all 3 of those, and so contractions I can do by clicking here, or I can just press the C key on the keyboard as a shortcut. So if I do that, we end up with a matrix which you'll recognize as a poly X matrix. And finally, we have a matrix with 2 indices, but there's a self edge connecting the 2. So a contraction on this will compute the trace of the matrix. So we'll end up with 1 plus 5 plus 9, which is 15. So I have another example I'd like to show from this article by Biamonte and Bergholm. If we go to page 7, there's something called example 4, where the article talks about how we can take a CNOT gate and decompose it or factor it into 2 tensors. And each of these tensors is rank 3. So I've prepared the definition of those 2 tensors in a text editor. I'll just copy that and go back to TensorNetCanvas, and I'll paste that text into this box, and I'll hit delete all just to clear the canvas. We can create the tensors that are defined here. We end up with these 2 tensors. So these are the 2 tensors, the COPY and the XOR tensors discussed in that article. And I've given names to the indices. So the first index on this one's called control out. The first one here is called control in. We can connect those two indices. And now if we contract these, we end up with a 2 by 2 by 2 by 2 tensor. And this corresponds to a CNOT gate. And to see that, we need to convert this into a matrix. We need to reshape it into a rank 2 tensor. So to do that, we need to merge some of the indices together. But before doing that, we need to make sure that the indices are in the correct order, or that they're permuted correctly. If we look carefully at the names of the indices, what we end up needing to do is grouping the out and the in indices together. And essentially what we want to do is swap the two indices in the center. So the way we do that is we can right-click on one of the indices, and we get this little menu that pops up, and there are options to transpose. So that means to move or to permute the particular index that's under the menu. We can move it either to the left or the right. And you can see as I hover over the two options, there's an orange semicircular arrow that gives us a preview of where the index is going to move. So I want to move it to the right, so it'll be on the other side of the index that's currently marked as number 2. If I click on that, you're going to see some of the elements inside the tensor will move around a little bit. So I'll do that now. You may have seen that some of the elements moved. And now if I hover, maybe you'll notice that the names have changed because the two in the center have been permuted. So now we can reshape this into a matrix, and we do that by merging the two indices on the left. So to do that, we right-click again, and we can say merge right. And over here we can merge left. And now we have this matrix, which you'll recognize as a CNOT matrix. So as another example, we can create a circuit inside MuqcsCraft or inside Quirk. Here I have MuqcsCraft. I can drag and drop gates onto a circuit until I'm satisfied with what I've got. So I'm just dragging a Toffoli gate here. Now I got my circuit. I'm happy with this. I can click on this to open up a little visualization of the state vector as it evolves layer by layer. Maybe I'd like to take this circuit and convert it into a tensor network. So I can take the URL, which encodes the structure of the circuit. I can copy this and go back to TensorNetCanvas. I'll delete everything on the canvas. I'll paste the URL in this box and then hit import circuit. The circuit we were just looking at, it has now been converted into a tensor network. Every tensor here corresponds to some part of the circuit. Now, just to explain a little bit more how we can select and move things around, if I click on a tensor, I can move that individual tensor. If I use Control left button, I can toggle the selection state of each tensor, and then if I click and drag on a tensor that's already selected, then all of them move as a group. So that can be useful for rearranging subsets of tensors. I can also hold down the Control key and drag with the left mouse button to select everything inside a rectangle. And if I drag back towards where I started, the software eventually decides I'm not dragging out a rectangle, I'm dragging out a lasso. So you can actually perform rectangle or lasso selection with the same button combination. Now that I have this network, I might want to contract it. And I could do that manually, pair by pair. So just by selecting two tensors at a time, I could contract them and keep going like this. And eventually I can contract the entire network down into a single tensor. But an alternative is to go back to the beginning here, the initial state. An alternative is to enter a special mode called step-by-step. So if I click on step-by-step, this panel opens up. I can hit the start button, and that will start a step-by-step mode. Okay, so if I click on that, now the user interface is locked up here. So what that means is I can still pan and zoom. I can still move things, but I cannot modify the network like I could before. Instead, the step-by-step mode guides me through incremental steps that will modify this network. And the button to do that is next step. So every time I hit next step, the software will do one of the steps in this list down here. So the next step is it's going to select two tensors, the next two tensors that it's decided to contract. If I hit next step again, it contracts them. If I hit next step again, it selects the next two tensors. And it keeps doing this repeatedly every time I hit next step. So how is it choosing which two tensors to select? It's doing that based on the policy that's in this menu. So by default, Minimum cost first is the policy used to decide which two tensors will be selected next. But if we wanted to, we could try a different policy, and we can continue hitting next step. I'll just keep doing that until we only have one tensor left. Now here, there's actually two tensors. One is behind the other. We can see that if we move things around. If I hit next step and next step, now we have a single tensor that's left. So I can hit F to zoom in. I would like to vectorize this. I would like to reshape it into a vector and compare it to what we see in MuqcsCraft to see if we have the same output. But before I do that, I need to make sure the indices are ordered in the same way. So if I look in MuqcsCraft, you'll notice that there's some orange highlighting on the wires when I hover my cursor over the wires, and there's also orange highlighting that shows up on the binary digits here. So keep your eye on this. If I put my cursor up on the top wire, the rightmost bit in the bit strings is highlighted in orange, right? And here it's the leftmost bit. So this is to indicate to the user that the first bit here is qubit 2, and that's qubit 1 and qubit 0. So we want to have the same ordering of indices here before we reshape the tensor into a vector. And if you look at the labels below the indices, we've got qubit 1, qubit 2, qubit 0. So we need to exchange the first two indices. We can do that with a right click. Actually, I can't right click right now because I'm still in the step-by-step mode. So I have to hit stop to exit the step-by-step mode. Now I can right click on this index. I can transpose it to the left. Okay, and you may have noticed the elements changed position. And now I've got qubit 2, qubit 1, qubit 0. Now I can vectorize, I can reshape into a vector, and I do that by merging the indices. So let's take a look at the first amplitude in this vector. -0.5i, that's an amplitude. We can convert it to a probability by taking the magnitude and squaring it. We get 0.25. That is precisely the probability being shown here. And then if you look at the glyph here, which is angled downward, that means the amplitude is a negative imaginary number. So we have the same amplitude in the first position of the vector. And if you compare with the others, you can confirm that all the non-zero amplitudes here match up with the output of MuqcsCraft. So another thing I can show is we can delete everything and import the circuit again. And it might be interesting to notice that whenever we have two tensors selected, there's an indication here of the cost of contracting those two. So here it says cost is 4. If I select, say, these two, the cost is 32. It's quite a bit higher. So we could either contract this network manually, choosing whichever tensors we want to contract next, or we could do it with the step-by-step procedure. And as the tensors are contracted, every time there's a pair selected, this will tell us what the cost of that contraction will be. And every time we actually do a contraction, there's a cumulative cost that will be incremented. So if we keep doing this, this cumulative cost will count up. Just to go faster, I'll enter the step-by-step mode with the minimum cost first policy. So I'll just hit next until we only have one tensor left. And now the cumulative cost is 232. So if I exit step-by-step mode, delete that, import the same circuit again, now I'll change the policy to be maximum cost first. So this is sort of the opposite of a greedy heuristic. And I'll go step by step again. So now it's doing these really terrible contractions where the intermediate tensor will get very big. And we can just keep going. And now the cumulative cost is 5,000. So one last thing I'll show is in the web browser, we can open up a console. So now I have a JavaScript prompt, and I can actually paste in code here and call subroutines that are defined in the code of TensorNetCanvas. So I've prepared an example of that in my text editor. If I just grab this code, I can paste it into this prompt. And what this code does is it instantiates three tensors. The first two are vectors, the third is a matrix, and then it does some calculations using those tensors, using, in this case, it's the einsum subroutine. So then we get the output of these four einsum operations.